I was working on the homeworks
Okay,
and
and WebAssign or the measure two?
WebAssign.
Great. All right, so let me grab into that. Which one are you working on?
Well, I did the two that are due on the 28th.
Okay, good. So that's 3-1 and 3-2.
Yes.
All right.
And I had a question about the one that does let me find it. I think it's at the bottom.
Well, which section? 3-1 or
It's
3-2?
in 3.2
Okay.
and it's the last one. It's number 9.
Number,
Number 9.
I see 12.
Oh,
Are you sure
oh,
it's
that's not the last one then.
okay, but it is number 9.
Well, yeah, but I guess 12 is the same kind of thing. But yeah, it's number 9.
Okay, I'm going to share my screen and we can look at it together. Now yours might have slightly different you know, numbers. Like, does yours, would you want to read your statement S and we can compare it to mine?
Yep, I have it up. It says for number 9, let statement S be the following. For every integer d, if 8 divided by d is an integer, then d equals 4.
Okay, so that one is actually the same as mine, isn't it?
Yep,
Oh, okay, I don't know if you're reading mine or yours. Okay, so they
yep,
might
I'm
put,
back with you now.
okay, they might put the number 6 over D, or they might, put the number 12 over D. But the point is, they're saying for all integers D, or for each integer D, it kind of feels better to say each or every with the singular integer. If, something, here they use 8, but again, that could be a different number for different people, over D is an integer. And that basically is saying if D divides 8,
Mhm.
then D equals, and in mine it says 4. But they're trying to make a point here. And the point is that 8 has more non-trivial divisors than just 4. So which is the contrapositive of this statement?
I worked it out before I got on.
We can,
So
okay,
I made a key. I
okay.
I had P equals 8 divided by D is an integer.
So you let this part be P, okay?
And then I had D equals 4 is Q.
I like it. That's so smart to make a little key where P means the hypothesis and Q means the conclusion. So
Yeah.
here we've got, some kind of quantifier for all integer D. P of D implies Q of D. We'll just say P implies Q. All right. So what would the contrapositive look like?
I wrote out not Q implies not P.
Uh-huh. And then we just have to remember that we learned that every conditional
Um,
is an all statement, right? Is universally quantified. So the contrapositive is going to have this for all integers or for each integer D part as the beginning, okay?
yes.
And I don't, and I think they give you a couple of their exist in integer D choices, but you
Yes.
just want to remember the contrapositive is still an if-then statement. So it's still going to be a universal statement. All right. And then what did you write?
Can I ask a question really quickly?
Of course.
Excuse me. We don't bother the quantifier or the I guess the element or the set. So
Well, when you
we
say
have
don't bother, when we're finding the sister conditionals that are universal,
yeah.
also we don't change the quantifier and we don't change the variable and we don't change the domain. But if we're writing the negation, we would flip the quantifier, but we still would not change the variable or the domain in the negation. But here we're not being asked to write the negation, are we?
No, we're not.
Okay. But you're right. We're not going to flip the quantifier because this isn't a negation, it's a contrapositive, and it's going to be, universal because
Okay,
it's an if then.
I see. Okay, so we focus on the conditional and we find its contrapositive.
Right. And
Okay.
and the contrapositive is itself a conditional. It's not the original conditional, but it is certainly a conditional. It's an if then. So let's
Um,
go ahead and write the contrapositive now.
I wrote if D is not equal to 4,
Good. That's the not Q. Good.
then 8 divided by D is not an integer.
That's right. Because here the word integer is being used as a property, not as a domain.
Mm.
So the statement 8 over D is an integer has a negation. And if it's not true that 8 over D is an integer, that means it's not an integer. 8 over D is not an integer. So that's exactly right.
Okay.
So, when we come here, we have these choices, right? Um, but we know that it's this last choice because that's the one where we've negated what you called Q and put it as the hypothesis. And we've negated what you called P, 8 over D is an integer. You called that P, which is really smart. And there's its negation that 8 over D is not an integer, is not P. Perfect. All right.
Uh, I went on to look at I think they have the converse and the inverse.
Okay. And now did you get the,
I
uh,
did do D.
okay, is D, okay, enter a value for D that will help answer the question. We can go ahead and do that. So, because the contrapositive has the same logical equivalence, it's logically equivalent to the original. And the point is there are other D's that make that predicate 8 over D is not an integer.
So because there are other values for D,
That's right.
um, that proves this wrong. I wanted to say it
That's
better,
right.
but
Because you can
okay.
find a D that's not 4 that makes this 8 over D an integer. I don't know why they ask you to figure out if the contrapositive is true or false. It's actually just easier to look at the original and figure out if it's true or false, in my opinion.
Because I noticed that the contrapositive was false for this, and the converse and inverse were both true.
That's right. The original is false, and the converse is the contrapositive is false because we can have that D is not 4 be true, but we can make 8 over D is not an integer false by finding a D that makes 8 over D an integer, right? So what would be a D that would work?
We could use 4.
Now we need to pick a D that's not
Oh,
4
oh, 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 I'm sorry.
because we
We
want
could
the
use
hypothesis to be true and the conclusion to be false to show this is false.
we could use 2.
Yep, you can use D equals 2 or 1 or 8.
Hmm.
Any of those would work, but 2 is certainly the obvious one because when we plug in 2 here, right, we're satisfying that the D we've chosen, D equals 2, is not 4. And we are also not satisfying the conclusion that 8 over 2 is not an integer because, of course, 8 over 2 is an integer.
Uh-huh.
So to prove this if then is false, we make sure that the hypothesis is true. That's why we couldn't pick 4.
Hmm.
And the conclusion is false. And right? Because that's
So
the
we're not trying to prove that the hypothesis and conclusion are false?
no, because remember, if the hypothesis is false and the conclusion is false, That if then would be true by false hypothesis,
Oh, wow. Oh, yeah, I remember that.
right?
Because
So
this is conditionals.
that's
Okay.
right. That's right. Very good. All right. So you did the inverse and the converse,
Yes.
and you figured out up their truth values. So do you have other questions about this?
Um, Only my question was mainly about the quantifier, but you
Oh,
clarified that P for a conditional, when we're doing the sisters, we don't change the quantifier.
because all of these sisters, the converse, the contrapositive, and inverse, are all if-then statements. They are all conditionals. They are all still universally quantified. And if you check the class notes, we went over that,
Okay.
right? Didn't, we definitely went
Oh
over
yeah.
over
Yeah,
that.
we did. It's just a little challenging because there's a lot of pieces
Sure
and they're
are. There are a lot of moving pieces. So here's just a fact to remember. Let's just make some notes here. If the original statement is A, and I'll put this in parentheses, it's always universal conditional. All of the sisters are also universal conditionals. We do not change the for all quantifier when writing the contrapositive, the converse, or the inverse of an original universal conditional. So that's kind of the first point. But then we can just also remember, but the negation of a universal conditional is an existential statement, and it's not a conditional, because if it was a conditional, it would be universal. But we know that the negation of a universal statement is existential, is an existentially quantified statement, and is not an if then, right? It's an
right.
end statement. So if the original, we can just go through this really quickly. If the original says, like, for all x in D, if P of x holds, then Q of x holds. Then the contrapositive and the converse and the inverse will all be for all statements because they're all if-then statements. But the negation is an existence statement, right? So the contrapositive will be for all x and D, converse will be for all x and D, inverse will be for all x and D, and they'll all be if-then statements, but the negation is there exists at least one x and D such that the hypothesis holds, so P of x, whatever it looks like, and the conclusion fails. And
Oh,
see, because if See, that's one of the ways that I try to attack this issue, that a lot of students are going to give me an if-then statement as the negation of a universal conditional. But it's never an if-then statement, because if it was, it couldn't be existential, because every if-then statement is universal. See what I mean? So this is just a way to help you remember, ooh, the negation has to have the opposite quantifier. It couldn't possibly be an if-then, because all if-thens are universal.
Oh,
So it just gives you another kind of a way to attack that issue of remembering that the negation is not an if-then. The negation of an if-then is not an if-then, it's an and statement. But all the sisters are if-thens. So they're all universal. They're actually conditionals themselves. They're not the original conditional, but they are conditionals. They're if-thens. Does that help?
yes. Yeah, that's nice and clear.
It's good to review all that. And you're right, there are a lot of moving parts. What else would you like to look at?
You mentioned a few minutes ago that we have the hypothesis and the conclusion,
That's
but
right.
for this form of statement, I guess, we have the quantifier, then the variable, and then it's set, or the element and it's set, and then we have a conditional statement. So the first part is
This is the quantification. This is information about the variable. It's the quantifier, the variable, and the domain.
okay.
But this is still the hypothesis,
All right.
and this is still the conclusion.
Okay.
So because you know, we start real simple in the class. We start with just a little p and a little q. There's none of this capital stuff with variables. But now we're trying to deal with predicates where there's a variable. And if you go back and look at the definition of a statement versus a predicate, and we practiced it way back when, 2.1, um, we just first started with P implies Q. This was the baby way to do it. But now we are talking about statements involving variables. Technically, those are predicate statements, and they're not actually statements until we plug in a value for the variables. Once we know what X is, here, here, and here, it's the same X. But once we actually insert a particular value for the variable X, then this predicate becomes a statement that we can evaluate in terms of its truth value.
Can we talk about informality for just a second?
Versus formality,
This is formal what you're doing right now.
what we're doing right now is formal notation. We're using symbols and like element of and the upside down for all, or the there exists, right? And there are different kind of there are different degrees of formality. And that's and the author, kind of shows you different degrees of formality. Let's go through a couple of examples. And but the minute you start using any kind of symbol uh instead of a word, you're working in formal language. So if we just look at, an example, all real numbers have real squares. That is completely informal because it's written with no symbols of any kind, right? But we could, you know, make it a little more formal, for example, by introducing maybe one symbol, like an X. And you know what? I think I'm going to put an each here because each and all are the same. I just want to make it simple. So each real X has a real square, X squared. Now this is slightly formal.
This is not a conditional.
We could write it as a conditional.
Oh, oh, I see. For
Okay.
every, oh, I'm sorry.
Yeah, go ahead. How could we write it as a conditional?
For every real, oh, no, no, no. If X is real,
Yes.
then X has a real square.
Yeah. Or we could say then X squared is real. Either way.
Oh,
So this is slightly formal because we have introduced a variable. But we can make it more formal. We can go, we could say for all X in the reals, X
oh.
squared is in the reals. So now, we're very formal. We don't have any words at all, really. Or we could write it like this. For all X in the reals implies X squared is in the reals. That's very formal.
Mhm. Excuse me.
And what we're going to learn tomorrow in class with our Tarski world, and you can take a peek. I've already posted some measure to material for chapter 3. It's very formal. Tarski notation is very formal. We can
So,
look at another example.
so if we did the sisters for that statement, we would
Ooh,
only change what's in the parentheses for E,
that's right.
even though we have the element symbol and we have domains.
Yeah, let's write the contrapositive of E. It would be for all X squared not in the reals implies X is not in the reals.
Hmm.
Now I have suppressed giving a domain here because we're not going to talk about the complex numbers, but the complex numbers subsume the reals. In fact, the complex numbers is the biggest set of all. And inside that set lives the reals. And inside the reals live the integers.
Complex, that's A plus BI?
Yeah, the complex numbers look like A plus BI such that A and B are in the reals. And what do you know about I?
I is imaginary.
Yep, it's the square root of -1, which is imaginary.
Ah,
Now, when you let the B equal 0, then we get the reals, which is just A, such that A is in the reals, because this component, called the imaginary component, disappears when this coefficient, B, is chosen to be 0. So
ah.
every real number is a complex number. All the reals live inside the complex numbers, right? Every real is complex, but not every complex number is real. Like, right, the number I sits out here. It's not real. It's complex. And there are
Wow.
real numbers that aren't imagined, they're not complex properly. Every real is complex, but we say it's not a proper complex number. This doesn't have an imaginary component. I guess that's the way I would put it. So pi is real. It's also a complex number, but it's a complex number that doesn't have an imaginary component because b is 0. This is 1. This is excuse me, a is pi and b is 0. And
Wow.
integers, there are lots. See, pi isn't an integer, but 3 is, and 3 is still a real number.
Wow. I've been familiar with complex numbers, but I never understood it like this before.
It's good to see a perspective. Yeah, the complex numbers are something special.
Wow. Um, I don't know that I have, I mean, I could I could pick at stuff all night, but I don't think I have anything that, that um I need further explanation on.
Okay, all right. If there's some topic, that you just like to discuss or go over, or if you want me to make up some problems, um,
Could we talk about negating quantified statements where there is a more complex conditional?
yeah, that's a good idea.
So we would need to use De Morgan's law for the conditional, and then we would have to change the quantifier.
That's right. Actually, we can play the sisters and the negation game.
Okay.
I think you had this in WebAssign, but it's good to do it again. Consider this conditional.
One of the WebAssign questions gave a
Uh-huh.
set. It gave a set, and it asked that we determine certain conditionals based on that set.
Right. Okay. So were there two variables or one?
Uh, I remember this, it gave this, I, I don't remember. I think it might have been two variables, but I know seeing the set was really helpful because it kind of tied everything together.
All right. Let's let D be this set.
Okay.
Consider this domain for X and Y. We'll let X and Y both be in D. Now consider this conditional. We can play with, we can do a sneak preview into tomorrow, actually. All right. So for all X in D, let this be A. If X is greater than or equal to -2, then negative X is in D. All right. So let's write the negation. Oh, it's not compound though. You wanted a compound uh
Well, this is good.
okay.
This
All right. So we'll do this one and then we'll do a compound one. Yeah, because we kind of shifted gears because you started about seeing a set. Okay. So what's a negation?
All right, for the entire statement, it would be there exists an element X in the set D.
You can write the phrase such that, or you can just put a comma, either way.
Okay, such that X is greater than or equal to -2.
Right, because our P of is X is greater than or equal to -2, and our Q of X is this statement.
When you write P of X and Q in X, what you're saying is X satisfies the condition P?
Yeah, it's a property of X. The property of X
Uh,
here is that it's greater than or equal to 2. And this
uh,
also is a property of X. It's that -X is an element of D, but it has something to do with X. The variable is X, so that's why the X is there. These are predicates. Both of these are predicates, and this entire thing is a big predicate because we have
oh,
an X, but they are properties. You can think of predicates as properties.
oh. Such that X is greater than or equal to -2 and uh let's see. X is greater than or equal to. And so we would negate Q of X.
That's right.
So it would be not X is an element of D. I'm trying to think how to say it in just normal language.
Yeah, okay, so let's just think about it. If it's not true that -X is in D, then -X is
Is
not
not.
in D.
Oh,
I mean, isn't that what it means to say it's not true that -X is in D? It means that -X is not in D.
yeah.
Uh,
Yeah.
okay, so tell you what, let's do another one. Here's our original. For all X in D, there exists a Y in D such that X plus Y equals 0.
Wow.
So now we've got two quantifiers and two variables, and here's the property of them. So this is like the P of XY. It's a property that has to do with both X and Y, and we have two quantifiers. This is kind of a sneak preview,
Wow.
okay? So we can write the negation. So the rule is just what you think it is. We can write it out. If it's not true that for all X in D, there exists a Y in D such that X plus Y equals 0. That's not true. All right, so here we go. This not is going to come all the way through. Just like here, what we really did was we negated, we didn't write it, but we negated for all X in D, you know, if X is greater than or equal to -2, then -X is in D. We negated that. We brought the not through and we flipped the for all to there exists, and then we negated this, P and not Q. Well, it's the same kind of thing, even if you have two different quantifiers. This means for each X in this set D, we should be able to find a Y that exists for that X in this set D to make this predicate true.
Wow.
That, that's the way we're going to interpret it. For all there exists. For all there exists means for each X and D, you kind of look at them one by one. We look for a partner Y that exists to make this work out, the predicate work out. So if it's not true that for each x in D, there is some y in D to make the predicate true, then what that means is there is at least one x in D such that for every y in D, this predicate fails. So this not comes through and it flips the for all to there exists and it flips the there exists to for all. And then we have to negate the predicate, right? This, this is the predicate. We're going to have to negate it. Just like this was the, we had to negate if P then Q, right? We had to negate this whole thing. And that's how we got this, which was the negation of if then. So now we'll just keep going and we'll finish it. There exists at least one x in that set D such that for every single y in that set D, x plus y is not 0.
Wow.
So let's see, which one do you think is true? Either the original will be true or the negation will be true, right? One of them's got to be true because they have opposite truth values, right?
Right.
So
I
what do you think?
I think the original is false
Why?
because the original, uh, the values don't appear to meet the criteria. I don't
Yeah.
know.
Well, yeah, you're right. Which can you give me a value in particular that doesn't seem to have a y that exists? Because the original says for every single x in D, so you can go one by one and look at them. For
Hmm.
each one of those, we should be able to find a corresponding partner, in some sense, y, that will make this true. And y's got to live in this set D as well. So,
If x is -3, then there's
right.
no way.
So look, x equals -3 is the x that exists in D, such that for every y in D, this fails, right? When x is -3, it doesn't matter which y you look at. You can look at every single one of these and try it out for size, right? For every y, -3 plus y will not equal 0. So you're right. The negation is true. The original is false. And we would try to justify it. X equals -3 exists in D, right? It exists. If we look at every y in D, x plus y not equal to 0 always holds. We would,
Wow.
right? We would need we would need y to equal 3 to be in D, but it's not.
Mhm.
It's not there. It's hard to see set D. I mean, it works out. If I hadn't put this -3 in there, then it would have worked out. For -2, we could find a partner y equals 2, right? Like if the -3 wasn't there for each x, like x equals -2, we could find a y. Like for -2 equals x, we would pick y equals 2. For x equals -1, what would we pick for y?
We would pick one.
Right. For x equals 0, what would we pick for y?
Can we use 0 again?
Yep, because nobody said x and y had to be different.
Ah,
For x equals 1, what would we pick for y?
-1,
And for x equals 2, what would we pick for the y?
-2.
Right. So this would all, the original would be true except for the -3. right?
That's why the negation says there exists one, so like even
At
just
le-
one.
Yep.
Ah,
Could be more than one, but all it takes is one. Like I could have put -4 in here as well, and that would it still would have been that the negation is true. We could have had a couple of different ways to prove the negation is true. We could have picked -3 or -4, right? But now, do later, same set D. Here's the original. For all x in D, there exists a y in D. No, 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 no. I don't want the same set D. I want a different set D. In fact, I'll call it G. G equals -2, -1, 0, 1, 2. Okay. So for all x in G, there exists a y in G such that x plus y. Oops, I closed that up too soon, equals 0. And so you can write the negation, and then which is true? Is the original or the negation true? One of them has to be.
oh.
And you did ask about quantified statements that have compound conclusions. We can look at that. And did we lose Sunita? Oh,
Maybe.
I feel terrible. We lost Sunita. Sunita. Compound components. Consider this statement. For all students, S. If S studies math, then S is a science major or S is smart. So we have a hypothesis P of S. We have a compound conclusion Q of S. And then we could play a couple of games. We could say, write the contrapositive, and then we can say, write the negation. Let's try those two.
So this is a if-then statement.
Uh-huh.
So, um, so we could use P and Q as our key.
Sure. So that's kind of what I'm doing here. I'm letting P of
Uh,
S be S studies math. And yeah, we could use yeah, we could actually break this up into uh oh gosh, R of S or Q of S or R of S. Would you rather do it that way?
yeah.
All right.
And we're breaking it up because it has the or operator, right?
Yeah.
Okay.
So Q of S would be S is a science major, and then R of S could be S is smart. All right. So
Okay.
what's the form?
So we keep for all students S.
Yeah, so it's for all students S. I'm just going to write this. This is that P of S implies Q of S or R of S, right?
I.
That's the formal original. And that will
Okay.
help us. So do you want to write the contrapositive formally and then write it informally?
Yeah,
It can be really helpful to use this key that you've made, right? All right, so the formal contrapositive.
it would be for every student S.
It looks like for all students. I'll
Oh,
say.
oh, 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 oh.
No. It's okay. It's no big deal. For all students S. I was just laughing at my writing.
Okay, so
Oh,
it would be, oh, I'm sorry.
go ahead.
S is not a science major. No. What am I doing? I'm sorry. No, this is the contrapositive. If S is not a science major and S is not smart. Okay, I'm
Right.
sorry.
No,
So,
you're fine. In fact, I want to do this in red. Why don't we do it in steps?
okay.
For all students S, because you're there. You're fine. You got it. For all students S, if it's not true that Q of S or R of S, then it's not true that P of S, right?
Oh, yeah.
Yeah, you're doing it. You're doing great. You already are distributing the knot across here, but right?
Oh, I
Wait
see
a
how
minute.
you.
Wait a minute. Wait a minute. Do I have extra parentheses here? I've got an extra parentheses here. No. We're okay. We're good. We're good. This one goes with this one. We're good. See, this is now kind of like the big Q, you know?
Oh,
But you were doing fine. So now we have to negate this because that's, the not conclusion.
so
Please.
that would be
Yeah, and you said it. You said it right. Not Q of S, right?
and oh yeah, and not R of S,
Yeah, you had it. So that's now the hypothesis implies not Q.
not P of S.
All right, and now I think you actually so now we can write it informally.
Okay, all right, yeah, okay. Um,
Because you were there, you were doing it.
but I confused myself. I skipped the formal part. I think it's easier to do it the way you did it.
It might help some people, yeah.
Um, so for every student S, or for all students S,
Or for every student S, it's fine. That you can change plurality, no problem.
if S is not a science major
If S is not a science major,
and S is not smart,
uh-huh.
then S does not study math.
Yep, you did it. It's probably confusing to have both of those, but it's either one is correct. Now, there's something wrong with this. And what's wrong with this is what Tarski recognized. This is a loaded example. It's talking about somebody being smart, right? It's talking about studying math or science. And he had this idea that he did not want to give examples. That's exactly why I gave this. that had anything that would make any students feel in any way weird. See what I mean?
Mm.
Like just writing this, could make a student feel weird. Right? I mean, so he was really ahead of his time as far as being politically smart and understanding what's important for students to take away from their experiences. And one of the things he realized was that math professors are human, logic professors are human beings. And, sometimes we grab an example that might make somebody uncomfortable. I've got a colleague, even now, we have kind of an ongoing argument about something called binary relations, where two objects are related to each other. And he likes to use this example where uh, X and Y are related if X is the father of Y, right? Or something personal like that.
Mm.
And I'm like, well, what if you got a kid that doesn't know his father? Why would we be talking about, fathers or smart or, to case in point, okay? So what he did, Tarski, he's brilliant. He said, okay, we can teach all of these concepts. We can teach them all. Is it just me or is this look blurry? Anyway, by building a world with completely inanimate objects, triangles, squares, and circles. And we can teach everything that we need to know about logic in this very kind of clean, unemotional world called Tarski's world now. And that's a better way to teach logic than to draw on anything that would be politically charged or emotionally charged or anything like that. And so this is what we're going to look at tomorrow. This is an example of every Tarski world is different, but they're always grids with these shapes in them, and the shapes have color. They're either white or gray or black, or they might be in the book a white or light blue and dark blue. It just depends. And
Wow.
each object has a letter name, and that's the identifying or key attribute. When you do a database, you have some kind of key attribute that absolutely identifies the data associated with it, like your social security number or something. Well, here the key attribute is the name of the object. And so, oh, look, there's something hidden there. Look at that. Oh, that's cool. Look, see that E there?
Uh-huh.
It's hidden behind some in my file somehow. And I can't see it because it's hidden behind that triangle. That's hilarious. But these are all letters near the beginning of the alphabet. And then they have shape, color, a name, and they have relative position relative to the other objects, not absolute position. It's not like, this is a grid, and we could say, hey, this first square is in row one, column one, so we would call that the 1, 1 location, and then A is in the row one, column three, so it's the 1, 3 position. No, no, it's relative position. Like A has a position relative to B and C. A is above them both. Even though it's
Oh.
not in the same column, since it's in a row that's above B, we say A is above B. Anyway, so or left of, right of, above, below. So here are some examples of some statements, and we can practice working with quantifiers by looking at each statement one by one and negating it first. Just write the negation. Don't just write a not in front of it, but bring it through using De Morgan's laws or any other rules that we know. And make sure you address the quantifier and, and then give the truth value of the original statement and justify it. So here's one. The number 6 is easy because it only has one quantifier for all. This says for all X and all these variables that aren't at the beginning of the alphabet, like X and Y. So notice how they're italicized. and they're not bold print, that's to distinguish them from the names of the objects, which are in boldface print, like F is a particular object. It's that square F. And H is a particular object. It's the circle H. See what I mean? And so the X's and Y's are variables. Maybe W would be a variable to distinguish those letters from the actual objects. So this number 6 says for all X, circle X, which means X is a circle, or X is not below G. See, this is very terse notation. This means not below XG means X is not below G. The X goes out front because it comes first. So is it
Oh,
true for all X that either X is a circle or X is not below object G?
that is true.
That's right, because you can look at the X's one by one and you can think, all right, there's some circles and then there's some other shapes, right? The circles are down here, but they're below G, but they satisfy circle X, right? The other
Uh-huh.
objects are like E and F and G itself and D and C and B and A. And all of these other objects up here satisfy that they're not below G.
Oh, wow.
So you have to look at every X and make sure that this predicate, which is a compound predicate, is satisfied for each X. And so it does make sense to kind of just separate the objects into two subsets. Either X is a circle, in which case it satisfies circle X, so it satisfies this or operated, predicate, or X is not a circle, in which case X is not below G is true. So you have to write something there.
Wow.
Look at look at 3. There's not even an apparent quantifier, but we know something about if-then statements. What is the implicit quantifier?
If if one if if there's I don't know.
It's an if-then. So what do we know about every if-then statement?
Oh, it's universal.
It's actually universal, even though that for all X isn't written there. We know that because it's universal, there really is a for all X there. So when we
Oh,
write the negation, we're going to say there exists an X that satisfies this hypothesis and does not satisfy this conclusion.
why did you say does not?
Well, in the negation,
Oh,
if you
oh,
were going to write the negation, it would be there exists an X such that P of X, so right of XH, and, right, the arrow flips to an and in the negation, not square X, which is the negation of the conclusion. Did I say hypothesis before? I meant to say conclusion. P of
oh.
X and not Q of X. Q of X here is that X is a square. Anyway,
So,
is it true or false? Is it true that if X is to the right of H, then X is a square?
yeah,
All right, where's H?
there's H.
So if X is to the right of H, is
Oh,
X always a square?
does it have to be on the same row?
No, no. Right of
Where's
means anything that's in a column to the right of H. Remember I said that A was above B, even though it's not in the same column? Well,
right?
right of doesn't have to be in the same row. So if we look at like B, what's to the right of B? A is to the right of B because it's in a column that's to the right of the column that B is in. C is obviously to the right of B, but D is actually considered to the right of B, and so is F, and so is G, there, and so is I. These are, but H is not to the right of B because H is in the same column as B, and E is not to the right of B, obviously. and B is not to the right of itself.
Oh,
But A, C, D, F, G, and I are all to the right of both B and H. In fact, they're all also to the right of E.
that means it's false because it's not just a square.
Yeah, so that means there exists an X such that X is to the right of H and X is not a square. See, that satisfies the negation.
Oh,
So you just pick an
so,
X, what's your favorite X that satisfies that it is to the right of H and is not a square. You pick your favorite X that satisfies the negation.
so we have to do a negation. That's really important.
It is because it's going to help you determine what's true. It can be a lot easier sometimes to figure out whether the negation is true or the original.
Wow,
So we're going to play that game tomorrow. And this
sounds
works,
interesting.
isn't it fun? And I
Sounds
love,
interesting.
right? And I love that it is not loaded up with, emotional stuff. You know,
Uh-huh.
I think he was a really brilliant logician to come up with this beautiful, clean kind of thing. And see, and I would never normally write, something like this, right? But wanted to make a point that it's really easy for professors to come up with examples that maybe just aren't even that appropriate, right? And Tarski was like, nope, 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 we're not going to do this. We're not going to play politics. We're going to live in a clean world called Tarski's world. And I really respect him for that.
Thank you, Professor. This was really interesting.
I always enjoy office hours with you. All right,
Thank you. Have a great evening.
you too. Good night.